Hello everyone, and welcome to the tinyML Vision Challenge. So this is the very first project we do in the tinyML Foundation in collaboration with Huckster.io. And the idea of this project is really to promote new use cases and new applications of tinyML Vision. So my name is Evgeny Gusev. I am from Qualcomm and also tinyML Foundation. And I'm going to be hosting you today. So we will host Himax and Impulse today. These companies are sponsors for the tinyML challenge, and their sponsorship goes beyond just financial contribution. They also provide the technology and the tools and the dev boards for people to use. So the session today is really to show how to use Himax and Impulse technologies to develop tinyML vision applications. So it's going to be more like a Q&A and informal discussion. So if you're interested in using this hardware and the tools for your vision challenge, this will be the session to follow and to understand. And again, we'll have plenty of time for questions. So before we start, it is a pleasure to acknowledge our sponsors for the tinyML Vision Challenge. So it's ARM, Impulse, Himax, Intel, and Qualcomm. They are executive sponsors. And the platinum sponsors are Lattice Semiconductor, Pixar Imaging, and Synsense. So this challenge is open until the end of August. And so if you're interested in contributing or in sponsoring, there is still time to do so. And as I said earlier, the focus of this vision challenge is to develop new use cases and applications for tinyML vision, because we believe that tinyML vision is one of the key applications for tinyML technologies for always-on low-power machine vision at the very edge. And also the secondary reason here is to educate the community, to promote tinyML technologies in community, and really connect the technology community to the developer community. So the submissions are open for another 2 months, and the winners will be announced in September. And there is a financial value for the winners. It is my pleasure to introduce our tutorial, our tutor today. So it's David Schwarz. He works for Impulse as a user success engineer, and David works with the community, with customer, and help them to connect and to develop their technology. So he's a perfect person for this discussion. And David, the floor is yours.
Thank you. So I'm really excited to be here today. We're going to be going through a tutorial on how you can create a computer vision and image classification application very easily utilizing the Edge Impulse platform, as well as the Himax WE-I evaluation board. And so if you're new to tinyML and computer vision, this is hopefully going to be kind of a way for you to take your first step in kind of seeing what it's all about, and maybe get you excited about new use cases and applications that you can think of to even submit for the contest. And if you're an experienced tinyML developer, but maybe you aren't familiar with Edge Impulse, this will hopefully serve as kind of an introduction to what we do and what value we can provide. So to get started, let me give a brief introduction of what Edge Impulse is. So we are primarily a platform for designing embedded ML applications. We support the entire pipeline of collecting data, designing your model, and any signal processing that you need to perform on your device. We help you test, validate, and improve your model. And we also handle deploying it in the field. And so our goal is to really enable these small embedded devices to perform these really powerful signal processing and machine learning techniques that previously were only available if you were connected to a data center or a server. And with that, with being able to run inference, classify an image, detect a person in frame, or detect an anomaly, or pick up someone's voice all locally on the device, it opens up a huge number of new use cases that just weren't possible before. And specifically in computer vision, you get huge improvements on power consumption. You don't necessarily need to be connected to the internet, and you have much lower latency compared to what it takes to send data to the cloud and then get a result back. So that's really what we're all about. And we are avid community members with the tinyML community. We support thousands of developers in their machine learning projects. And we have a number of industry-leading features that can kind of help you take your models and designs to the next level. And when we're going through the tutorial, I'll get into more detail on those. But we're really striving to be kind of at the state of the art of this really exciting new field with embedded machine learning and computer vision. So I'll kind of give an overview of what our platform looks like. We'll go into a lot more detail in this during the tutorial, but basically when you're designing a machine learning application, you kind of go through this flow of you collect, label, and wrangle your data. Then you go in and you're designing kind of your model, what you want to detect, what approach you want to take with that. Then from there, you have to test, tweak, retest, and kind of go through that loop with your model. And then once you're happy with its performance, you're going to need to deploy it to the actual device to run inference. So we support every step of the way, as already mentioned, and kind of starting with data collection, we're really proud to have a really diverse set of ways to get data into our platform that makes it as easy as possible to collect data, because that's often like the hardest step in the whole process is getting enough good data to make your model functional. And so we support, as we'll see in the tutorial, direct streaming from edge devices like the Himax board, uploads from other mobile devices like a cell phone, or pre-existing data sets that you've collected and formatted as either a CSV, JSON, or some arbitrary format that you want to send through our system. Once you have that data, we have tools that let you analyze and kind of see what you have, maybe find gaps in your data collection process. And then from there, we have what we call the impulse, which is a combination of the data pre-processing steps to take your raw data and get it into the form that your machine learning model will accept as input, and then the design of the machine learning model itself. And once that's complete, you have kind of a pipeline that allows you to take raw data and get a classification or a more rich kind of understanding of what that raw data was as a result. And that can run directly on the device. And so once you have that impulse designed, you then need to test it. And so we offer tools to both kind of develop an intuition of how your device and model will handle data in the real world by letting you live sample data. And we also support, we also make it very easy to test a large data set against different model architectures, impulse designs, and input data sets in order to kind of get a gauge of how your development is improving or changing over time. And then finally, we, as I previously mentioned, we support deploying to a variety of embedded targets, everything from an M0 core all the way up to a Raspberry Pi or a Jetson Nano running Linux. And for those deployment targets, we offer pre-built firmware for supported boards like the Himax. We offer a fully open source C and C++ library that lets you pull that into any existing project and then take the result of the impulse and add whatever application logic you want onto that. And then we also support other deployment options that work within different development frameworks that we'll see in a little bit in the tutorial. So that's kind of an overview of what Studio what Edge Impulse Studio is all about. And so now let's talk a little bit about the board we'll be using today, which is the Himax WE-I Plus evaluation board. The chip that powers this, the WE-I Plus, is a really powerful DSP core. It has a ton of memory and flash for storing and running machine learning models. And it's just really, really fast. As we'll see, it can do image classification in basically real time. And it enables a host of really, really cool low power use cases that aren't possible without that kind of acceleration. In addition, the board has a lot of sensors for when you want to go beyond computer vision. It comes with dual microphones, as well as a 3-axis accelerometer. And the camera on it supports up to 640 by 480 resolution. And the USB connectivity is, as we'll see in a little bit, is going to make it really easy for us to stream data into our development environment, as well as kind of get an idea of what the application is doing once we're running inference on the device. And so with that, I'll jump into the tutorial. What we're going to be designing today, I'll give a brief overview, is we're going to be designing an image classification app. This image classification app, the goal of it is that I have a carton of eggs that I bought from the supermarket, and I want to be determining if any of these are cracked or broken. So we're going to be sampling data, designing an impulse, and then testing out that model that's going to try and classify those things.
And David, before we start the actual tutorials, so a couple of questions, maybe you can answer them now, and then people can add more questions later. So one question was on the cost of the HM Plus platform and the cost for consulting, like if people want to use HM Plus, what would it cost them in terms of kind of getting the setup and also getting kind of support?
Yeah, that's a great question. We were just about to see, but the platform is completely free for developers. You can go in and create an account, create as many projects as you want. You get all the source code for the firmware, all for free. And then if you are, designing a more enterprise level app, we can work with you in a more professional context to kind of support and provide kind of dedicated resources for helping you productize your machine learning application.
And I think there was a comment addition from Jenny. She said that for enterprise, it's also per project type of basis.
Yes, that's a good point. Yeah, we do not charge per device. So, yeah.
And another question related to the Himax board, since we're talking about the low power vision here, always on vision there, it's good to know that the Himax board has quite a bit of capability there. But as far as the power measurements, is there like a power meter? Like if people want to see how much power the board and application consumes, how do they know? Is there a way to do it?
Yeah, so Himax actually provides on this board specifically, on this development board, it's a little bit trickier to measure power through the USB, but Himax also sells a more dedicated development kit board that allows you to connect current meters. And the power performance on this is really impressive. Himax actually ran a case study doing kind of basic person detection at 1 FPS. And for that use case, they were able to get image classification in only 100 to 150 milliseconds, which we'll see replicated here in our design. And then on top of that, at 1 FPS, that allowed them to operate at between, I believe, around 2.2 to 4 milliwatts of power consumption, which is incredible. That can run off of a battery for a really, really long time. Yeah, and so, yeah, that's kind of the power of this board.
So basically, you're saying there are two boards. One is kind of more basic version of the board for development, and then you have more kind of advanced version that people can get more to the guts. Okay.
Yeah, definitely. And if anyone's interested at the end of this, I'll go ahead and grab the link for the more. I already got the link for the development kit I'm using, but I'll post the more kind of fully featured DK that can be used with the multimeter current sensor.
Okay. Thank you, Dave. Please proceed with the tutorial part.
Great. All right. Oh. So let me switch over to the project. So I'd like to start at kind of the home page of our website at Edge Impulse. So here, like I said, you can create an account and get started completely for free. And then the first place we're going to look is kind of our TOPS level docs page. We have a really great set of documentation for how to do anything you want to do within Edge Impulse. And specifically, we're going to look at the support for the Himax board. So right here, we've got kind of a getting started guide that will help you go through, set the board up, and get everything installed. And so what I'll be showcasing right now is kind of just how our command line tools interact with our pre-built firmware. And this is going to help us come in later when we're trying to collect data and classify images off of the board within Studio. So if you go to this page from here, you can download the Edge Impulse firmware. When you download this and unzip it, you get a set of, you get a firmware image, and then you get a set of command line helper scripts that help you flash this to the board. I'm not going to flash this right now just because it takes about a minute to go through. But once it's installed on the board, it can connect with our CLI tools to either collect data or actually run inference with whatever model you've loaded. Now, this image as it exists doesn't have the computer vision model we want to be testing out quite yet, but it can still stream data. And so to interface with the data streaming, we just type Edge Impulse daemon. And so the daemon is the tool that handles data streaming from any of our supported boards over here to Edge Impulse Studio. So it's connected. Fantastic. And so from here, we'll be able to see in my project, which I just accessed through the Edge Impulse Studio once I've logged in. We've got the project and it's eggs AI. And so, like I said, what we're going to be trying to do is classify whether a carton of eggs is cracked or intact. And so to start, we can look at the devices tab. And so this is kind of just a log of every device that's connected to this project. And right now you can see that my Himax board, which I've got right here, is connected and streaming. And so if I now go to the data acquisition view, I can see the live feed from my camera. And it's a tiny screen because right now we're sampling it 640 by 480, but then sampling down to 96 by 96, but which I'll go into a bit more detail in a bit on why we're doing that. But there you can see my keyboard, and over at my kind of test setup over here, I've got this egg carton that I got from the supermarket, and we're going to be kind of testing out what we can do with this. So as you can see here, I can tell that this is kind of an intact specimen, and then this one is one that's been broken. And so I've already collected a bunch of data on this, and we can kind of look through what that looks like. So there's kind of a broken one, there's an intact one, and kind of that's about what the images all look like. They're kind of centered around the object in the middle, and then we're trying to detect if those kind of cracks are there. And so as we can see up here, I've collected 72 data samples, and I've got 2 labels. So we're only trying to classify between these 2 cases, which means we're constrained to see, we always in this case want to be looking at the egg carton itself. If we're not pointed directly at that, we're not going to get any useful data. But in this constrained case, you can imagine maybe if you were on a production line and you were specifically looking at the product you're creating, in a lot of use cases, you don't need more than just a binary classification. Just to go through some of the other options for collecting data, here we want to be collecting off of the exact sensor we're going to be running inference on later on. But we also support a whole host of different ways to get data input into Studio. So you can use a mobile phone, you just scan a QR code, and then you can use your phone's camera or the microphones or the accelerometers embedded in that. You can use your computer collecting data from, again, a microphone or camera. And then we also have this data forwarder, which can interface over a really simple serial protocol with any device. And so this is kind of how, if you're designing with your own custom hardware, you can get that data into Studio and then start working with it. And then finally, as mentioned, we have some ways to get pre-existing data sets that you've created, maybe through your own do-it-yourself machine learning pipeline, into Studio. All right, so with the data collected, we're now going to go to the next step. I think actually before we do that, let's actually collect a live data sample. What do we need more of? So we have a couple of more cracked samples than intact samples. And this is actually a good point to talk a little bit about what you kind of want to look out for when you're collecting data in your own computer vision application. So I'm going to go ahead and set that down. There we go. So as you can see, we've got this, oh, let me change the labeling on that one, since that was, I left the label as cracked. But, and so like you can just change the labels on any of your samples really easily. And so the first thing to keep in mind with your data set is you kind of want an even representation of all of the different labels that you're trying to collect. Because you want to give the model kind of equal exposure to all the different conditions that you want it to kind of work within. And so that also, in a lot of use cases, can come into play with more than just having two examples. So for instance, if I wanted to also detect if a entry in the egg carton was missing, I would need to add a third label, and I would also need to add in 30 or so more samples probably to get kind of a good representation of what that looks like to be able to train the model. The other thing we want to consider is that we want to be able to test our model against data that the model's never seen before. And so the way we support that in Edge Impulse is we have separate data sets between the training and test data. So in the test data set, these images are going to be of similar types and the same labels as what we are training against, but these exact images will never be looked at by the model when it's doing training. And what that helps do is help kind of compare how the model works after we've trained it in a real world case. And since you can upload a big data set of a lot of different images, this is going to let us later on, as we'll see, kind of benchmark how our model is doing if we change a few parameters or add more data in the training set. So with this all done, we're next going to go to actually designing the impulse, which is going to be where we create the neural network and where we do all of the pre-processing that we want to do beforehand. So the first step here is that since we're working with images, Studio has automatically detected that we have image classification data. And so from there, it's auto recommended me this kind of layout where it's downscaling the image to a 96 by 96 square. And this is mainly done first off, because at 96 by 96, we're still keeping a lot of the features that we want for this type of application. But we're also getting rid of a lot of the memory that's required to process a larger resolution image, both in ingestion, like actually collecting that larger image, and then during training, where we would need a bigger network to handle the higher resolution image. Furthermore, as we'll discuss in a bit more detail in a bit, we're going to be using a transfer learning block that's already been trained to classify arbitrary images in this 96 by 96 dimensions. So in order to kind of get the full use case of that, as mentioned here, we want to be using a case that is kind of already has the transfer learning data available. And I'll go into a bit more detail in just a second on how that transfer learning works. So the next step is our what we call processing blocks. And so in the realm of computer vision, we have a single unified image processing block. And the goal of this block is to collect features from the image that are going to be salient and different between the different classifications that we want to detect. And then we're going to input those features into the neural network. Because if we just directly input the 96 by 96 image into the neural network, we would need a huge neural network that took up a ton of memory and a ton of processing time, both in training and in inference, to kind of learn to detect these features. And so we'll go into a bit detail on what this is, but essentially we're using UMAP. And so we're going to collect kind of a three-dimensional representation of how these different images are related to each other in that kind of three-dimensional feature space. And so just to kind of give some more context beyond computer vision, if you're interested in doing maybe other types of sensors in addition to a camera, or if you're interested in kind of spectral analysis of an audio file or something like that, we have a whole host of features for audio, and then another set of features for kind of arbitrary sensor data. So any kind of time domain sensor that you're collecting, be it an accelerometer, a current sensor, anything like that, we have pre-processing blocks that help you extract the most useful features out of it to then feed into a neural network. And then, so when we get to the transfer learning block, we recommend that for computer vision image classification use cases that you kind of leverage this transfer learning. Basically, what this means is that the model architecture that we're going to be using, which is a MobileNet v2 based image classifier, and we'll have a few more details on that in a bit. But the transfer learning pre-trains that model on a huge set of images. And then when we come in, we just need to train for a much smaller number of cycles with a much smaller amount of data in order to get that model classifying the images we want it to classify. And so this is a widely used technique that's really, really effective, especially in terms of cutting down on your training time, which we'll see in a little bit. We will not have to train this model for very long to get it to be effective. However, we also support developing, creating an arbitrary neural network with Keras, and we even have kind of an advanced mode if you're tinyML expert and you just want to go in and write Keras code and have your model be created from that. We fully support that. But for the context of this demo, I'm going to be kind of sticking with the easy road where I just use the transfer learning and kind of leverage that in order to make this, a very short training time that I can show you in real time. So with that, I'm going to save my impulse. And we're going to go to the feature extraction. So this is kind of our image processing block. And here we can kind of see the raw data as it is in its 640 by 480 form. And then we also see the downscaled to 96 by 96. Once I save these parameters, it lets me generate my features with the UMAP algorithm. So it's already showing the generation. It kind of spoiled it since I've already done this, but I'll go ahead and regenerate the data just so you can see kind of how long it takes and what's involved in real time. But basically, what's happening here is that UMAP, which is just a common algorithm for doing this sort of kind of image feature extraction, is constructing a graph representation of how the data relates to each other. And then it is collapsing that down into a kind of lower dimensional, like in this case, 3 visualization dimensions, that is easier to work with both in terms of time complexity for our model, as well as just, looking at this, being able to intuitively understand what's happening. And that's my kind of, 1,000-foot view understanding. I'm no expert on UMAP at all, but what's really cool is that once we've done this, we can actually see a representation of how our different samples fit together in 3D space. And so it's really interesting. And in this case, we get these two kind of clusters of features that are relatively similar, but within those features, we have both labels. So this doesn't necessarily mean that the neural network won't be able to classify between the two labels with this clustering, but it can help kind of give you an intuition of how easy or how difficult something is to learn for a model like this. And then finally, within the context of the Himax device, which I've already told this project that I'm working with, it provides us an estimate of how long this process is going to take when we're actually taking a new sample on the device itself and then running inference on it. So we have to do this every single time before we provide the image to the actual neural network. And this is kind of the cost of doing so. So now once we have our image features, we're going to move to the transfer learning block. And so I've set this up with kind of some standard recommended by Studio hyperparameters in terms of the number of training cycles. So how many iterations we're going to go through training the model on our data set. The learning rate, which is how much the weights of the model are adjusted each time we go through a training cycle. I'm not using data augmentation, but data augmentation basically involves making small, almost imperceptible to a human types of changes to the image, at least in this case, in order to kind of help harden the machine learning model against small changes like maybe the saturation of the camera when it's working in the field or the lighting conditions that would make a very minor difference to us. But if the model has learned to detect the classification based off of those features, it won't be very effective in the real world when those conditions change. And so this can help if your data set is working in kind of limited conditions, like all the data I've collected is maybe with the same lighting, but thankfully I'm going to be demoing it in that exact same lighting. So I don't really have to worry about different lighting conditions or different environments, but this can definitely help out. And just to kind of give a bit more guidance there, with data augmentation, generally what you want to do is kind of try it out with your normal data set, see where the gaps in your data set are based on the model's performance in the real world, and then go in and say, okay, do I need to add more data? Do I need to augment that data in some way? Or is there something maybe else that I need to change in terms of these other hyperparameters? The minimum confidence rating is basically at the end of the neural network. Once it is said, okay, I think there is a 60% chance that this is an intact egg, then this is the threshold for which that's considered intact as kind of the final classification. So with these hyperparameters set, and again, Studio has kind of set these to basically default values that'll work pretty well in this case. And then from here, we have the model architecture. And so when we're doing this transfer learning, we have a set of kind of pre-built blocks that have different mobile net architectures. And these are just, think of these as just different combinations of layers in the neural network that are then trained on that transfer learning data set. And they have different trade-offs in terms of how much RAM they use, what resolution they're operating in, and what color scales they support. And so right now we're going to be using MobileNet v2 at 96 by 96. And then we can start training. And so while this is going, I'm going to kind of hop to a copy of the project that I've made that just kind of that already has this training complete. But as we'll see, this training is not going to take very long. So we can tab back to this project in just a little bit. But once training is complete, you'll be presented with this view. And so this view shows you three things. First, it shows you the model and its training performance. So the important thing to note here is that there are two model versions to look at. The first one is the unoptimized or float32 model. If you're familiar with traditional machine learning and computer vision on host systems, this is what you normally work with. This is the default that Keras or TensorFlow will output. And this is how the model was trained or is being trained over here. And look, it's already done. And so this is run for 50 epochs, so 50 training cycles. And then it's gone back in and done 10 different fine tuning cycles. And so I'll switch back to that while it's kind of profiling everything. But what's the problem with Float32 is that on an embedded platform, it's really slow to run inference with Float32 operations. A lot of ARM cores, if they have an FPU, it's still much slower than doing integer operations. And it also takes up a ton more memory. So what we can do, and if you're familiar with the tinyML kind of tech, you'll know this is a pretty standard thing to do, but you'll quantize the model, which means you scale down that range of floating point values down to a 0 to 255 kind of, or negative 255 to 255 scale. And that kind of gives you the memory benefit as well as the faster operations. And in a lot of cases, you won't actually see that much of a change in accuracy. So here, if we're looking between the quantized and unoptimized, this is a pretty good use case, pretty good situation for quantization where we don't really see a drop in overall accuracy. And it'll actually be interesting. We can go back here and now look at our model in the that we just trained. Which the difference between these two is basically just the data that I added in earlier when we were in the data acquisition view. But we can see the quantized and unoptimized models both perform very, very well. And in fact, they scored 100% on the validation data set. So that's testing it on a small slice of our training data. How accurate was it? And it got all of them correct. And so now we can kind of see the feature space again of how these different classifications are represented by the features that we extracted earlier. And we actually, we'll have to look here to see this, but we can actually get a view where we can kind of see where our incorrectly labeled samples existed in this space, which can be a cool way to kind of visualize like, okay, what maybe made this model kind of have trouble identifying that sample. And that's kind of just a way to help build up an intuition on how your model is operating. So we've successfully, hit 100% on our training data, but that does not mean that we're going to see 100% accuracy in the real world, as we'll see in a bit. But the final tab here is again an estimate of performance. So just like before, when we saw an estimate for how long it would take to do the feature extraction, now we're looking at how long is it going to take the model to run inference. And so on the Himax, it's awesome. It's only going to take 82 milliseconds. And it's only going to take a couple 100K of RAM. And if you remember, the Himax has like 2 megs of RAM. So it is all set to run this model. So once we've trained it, and we don't need to retrain because we've just gone through and classified things, we can now run live classification. And live classification is a really cool feature where we can take the exact same data streaming service that we were using during data acquisition, and we can start sampling from that sensor and then classify it with our model within Studio. So to clarify, this is streaming the data from the Himax to Studio and then classifying it here. And the advantage of that is that by doing this, we don't have to flash the device with any new firmware. We can just let it run. And so here you can see that I just took a quick snapshot of an intact egg. And then here we're looking at kind of where that data sits compared to our training data. And we are also, we also get the final category label from that. And so this is a great way to kind of spot check your model in real life. So in addition to this, we kind of want to do a more robust testing as well. So what we're going to do here is we have that kind of test data set that we split out from our training data back in the data acquisition view. And we're just going to run through and classify everything. And this is going to run our quantized model against every single test data item within Edge Impulse Studio. And so here again, we actually got perfect results within our test data set. And to be fair, this is a relatively small data set, and it's a relatively constrained case, right? Where in almost every scenario, the object we want is centered in frame, and it's either intact, which has a very distinct kind of signature, or it's cracked, which is clearly fairly easy for the model to tell. So in a second, we'll see how it works in the real world, but so far we're seeing really good results. And if you remember, it maybe only took me a few minutes to run training. And so that's kind of the power that the transfer learning gives us, as well as this specific use case being kind of generally pretty well suited for this type of camera and model. So the final thing I'll go through, and I don't want to take up too much time. I want to make sure we have plenty of time to answer any questions everyone has, but I'll just go through this real quickly and then show what the final deployment looks like. But here we have a versioning system within Edge Impulse that is designed to allow you to add your data, make a model, and then kind of iterate on that and compare performance between different versions, because, you know, maybe as we actually saw between the public, this prior version that I had saved and the version where we just added a new data item, they actually have slightly different performance. And that's just because there's slightly different data that the model was trained on, even if everything else is exactly the same. So that versioning lets you save the state of all of the data that you acquired, as well as your impulse and any other parameters that you had configured. And so then finally, we get to where we actually deploy our model to the edge device. And so as mentioned, so we support pre-built firmware for all devices that kind of can support a certain app. And so here you'll see we support a lot of boards, but within image classification, Studio is filtering out boards that can actually run the model that we've designed, because it's decently large and it takes a decent amount of computational power to run. So this is a pre-built firmware that's going to kind of do everything for us. It's going to run the inference, and then it's going to report the results to our serial connection. The other options are that we can deploy the model and its impulse as a library. And so this is if you were developing your own kind of enterprise grade or production grade app, this is what you would use to integrate it with all of your application logic. So to actually do something with that classification that you got. And then we also support kind of libraries within the Arduino and CubeMX frameworks for those types of boards. So once we've selected our target, which is going to be the Himax board, we're now going to go to where we kind of look at our final optimizations. And I've kind of spoiled this here because this has already been enabled. But if you remember back from our previous screen, our previous slides, where we had kind of our awards that we've gotten for the Eon Compiler, this is kind of a really cool and state-of-the-art, piece of technology that we've developed that is centered around really optimizing the RAM memory usage of these models when they're run on these, super tiny, usually memory constrained devices. And so essentially what the Eon Compiler does is that if you're familiar with how normal TensorFlow Lite models are run, there's generally an interpreter that is loaded in, and that interpreter then executes the different operations that it needs to run each layer of the neural network. And so in comparison, what the Eon Compiler does is it compiles those operations and the math that's required to kind of compute a given layer, it compiles that directly to source. And so by doing that, you save on the overhead of having to run the interpreter, as well as the overhead of having to copy as much data about the operations into RAM. And so as we'll see when I enable it, we get a free 100K of RAM and some flash, and it has absolutely no impact on model performance. So the latency and accuracy is exactly the same. And then the final thing to note, again, we're going to be using the quantized model. technically, since the Himax is so powerful and has so much flash, we could fit or so much flash and RAM, we could fit the unoptimized one, but its performance would be much slower, and our accuracy is so good with the quantized that we can use all of this extra RAM and flash to do application logic in some later design. And so let's build the firmware. And we'll see this just gets downloaded straight through my browser as a zip file, just like the kind of generic firmware that was available from our documentations page. And then from here, we can just unzip and we get the exact same firmware image and then a set of command line scripts. I'm again not going to actually flash this live. I've already flashed this exact same model that we just trained to the board, just because again, flashing this takes about 1 minute to 2 minutes. But what we can do now is we can quit out of our daemon that was collecting streaming data, and we can communicate with the board over serial in order to actually tell it to start running inferencing. So with that command, it's now classifying objects and it's telling me the result on a command line. So right now it's pointed at the ceiling, so it's not really working well, but let me set that up. So now we're looking at, I'm holding it over an intact specimen, and that one is showing really high confidence that it's intact. And so now I'm about to move it over to a cracked one, and we'll see if it can detect it in real time. Yeah, and so it was able to pretty quickly pick up that this is a cracked one, and then I'll move it over to another intact one. It's having a bit more trouble with this one. There it goes. So now it's seeing, it's about 60–70% sure that it's an intact egg. Great, so with that, we now have a working machine learning computer vision model. And that's about all it took. Of course, from here, the next step, kind of once you get to this point, I would really recommend that if you're interested in kind of developing your own application logic with this, that you go back to our documentation page and you take a look at our source code for this Himax board. So the source code of the run impulse program and protocol that I just showed you is completely free and open source. And from here, you can kind of take a look at like what's required to actually like take the output of the model and then actually go do something with it. And so this is really a great jumping off point into designing your own machine learning product. All right, so that about wraps up my tutorial. So for next steps, if you're interested in picking up the board, you can do so from here. You, of course, can at any point sign up for free and create a computer vision application at Edge Impulse. And then, come up with whatever interesting use cases and designs you can think of and definitely submit them. You have, again, all the way until the end of August to submit entries. And yeah, so I'll now do a short Q&A. And if there's anything we don't get time for, feel free to email me with questions, David@Edge Impulse, or ask on our forums. We have a great community that is that'll be able to help you with any questions that you have as well.
Thank you, David. There are several questions here. You answered a question earlier on the cost of the Edge Impulse development kit, which is essentially free for developers, and there is a special pricing for enterprise customers, and obviously they can contact Edge Impulse for this. There was a question on the cost for the Himax dev kit. Do you know how much the Himax dev kit costs?
Yeah, we can pull it up. It's around 65 for the DK.
And where people can get it if they interested at SparkFun?
Yeah, it's available at SparkFun.
SparkFun, yeah.
And potentially other distributors as well.
Okay, great. So there is a couple of technical questions. A question from Steven. can I use H-Impulse data acquisition to process image data from an MP4 file, not just from the Himax camera?
Yeah, definitely. So if this is an MP4 file that you've already collected, we have a command line tool. It's just called the Edge Impulse Uploader. And so you can just say Edge Impulse Uploader, you tell it what project you're working with, and then you can just send that data into your studio project. And then we also support recording that MP4 data live from your computer or phone, and then you can export that out of your project to do whatever data you want with it. So we kind of support both importing and exporting of any arbitrary kind of audio. Oh, wait, sorry. I misread that. Image data from an MP4 file. Right. I'm not actually sure on that. Jenny, do you happen to know if we support MP4 image input? Yeah.
Yeah, MP4 video.
Yeah, an MP4 video. So I suspect that, yeah, I suspect that for most of these, we're kind of operating right now on collecting kind of that image itself, and it's usually at a lower frame rate. So generally, you're going to get kind of the static image as your labeled data, but as Jenny mentioned, if you have an interesting use case that you need support for that, we're always happy to kind of explore options like that. And you can email hello@edgeimpulse.com with your use case and information about what you need.
Or post it on the forum, I guess, on the H-Impulse forum, right?
Yes, absolutely.
Yep. And there are links there. It's forum.edgeimpulse.com. That's the link. So there is a question from Sorry. Can we choose different algorithms for training or use our own algorithms?
Yes, that's a great question. And I actually neglected to mention a few cool features around that. So I already showed you that that you can kind of, well, I told you, I didn't show you, that you can create your own neural network block with Keras. And so anything you can do within the Keras framework, you can do here. So let me actually switch this out just so we can see what this looks like. So in the Keras view, you either have this kind of UI view where you can add your own layers, and we support different kind of common layer operations. And then we also have an expert mode where you can just go in and write Keras Python code, and that will be how the model gets generated, or the model architecture gets generated. And then in addition to that, we also fully support creating your own custom pre-processing block. So if you need to do some custom DSP, you can just add a custom block. And we have a tutorial on how you can kind of go through this process and do that. So yes, we generally do support kind of whatever your personalized algorithms and operations need to be, you can generally do it, yes.
Yeah, thank you, Dave. A couple more questions. There is a question from Dima. Is it possible to use an alternative camera module with Himax WE-I Plus? So the one you showed today is on the VGA monochrome, and he would like to get something more like 2 megapixel RGB, for example, OV5642.
So I'm not completely sure if you would be able to get 2 megapixels with RGB. I do know that the camera interface on the WE-I can support other cameras, but I would have to get back to you on if it would support that exact use case.
Yeah, there is a very interesting question from Dave. He's asking whether H-Impulse can support data from multimodal type of sensors, like, for example, binocular cameras or accelerometers or other type of things in a single sample.
Absolutely. And we actually, on the Himax itself, we have a really cool sensor fusion example. Let me delete these. So we actually ran a workshop where you can run the Himax with a bunch of humidity and CO2 sensors and run sensor fusion. Let me actually pull the GitHub link up.
For that. The short answer is yes. And
yes.
Practically speaking, how do they train their models and how do they run them?
Yeah, so this actually goes through the whole process. But basically, when you're uploading your data, we fully support, if you're uploading from a pre-existing data set, we support any arbitrary format of any fusion of sensors. And then if you're going through our own data forwarder, you can also define how your data is laid out in the format that it's being output from the serial connection. And that also supports multiple sensors. So for this example, that's in GitHub, and again, available open source, we were inputting CO2 and humidity data both at once. And so the only real limitation there is going to be kind of how much data. Like if you're trying to input, 2 high resolution cameras, you might run into issues there. But within the data, our data uploading tools is completely supported.
Yeah, that's what I was going to follow on. What are the limitations of this in terms of how many different modalities you can run at the same time? Is it limited by the number of modalities, or it's limited by the bandwidth, or it's limited by the memory on the device? I mean, what are the limitations? Let's say if I want to run both audio, video, accelerometers, temperature, humidity, these kind of things. I mean, are there any practical limitations? Or
yeah, so practically, you're pretty quickly going to hit some memory limitations if you are running through. So one thing I'll say is that if you were going to do this, you would need, I believe, separate processing blocks between the image and basically image and non-image data. And then beyond that, you're going to start to be consuming a lot of memory. And especially if you're adding other types of time domain sensors, those can be combined very easily and very well. You can use a unified processing block and just kind of have multiple axes, each representing a different sensor input. But when you add images on that, you're going to start seeing slowdowns in terms of your inference time and a lot more memory use. So that's kind of the main practical limitation.
Okay, well, thank you, David. 2 more questions. One is, do you have annotation / bounding box support available in Edge Impulse?
Yes, so we do support object detection. It's kind of in a separate, so as what we saw here is kind of specifically geared towards image classification for the entire image. We also support object detection, but due to the complexity of those models, right now we only support those on our Linux platforms. And that's really just a constraint on how big the model has to be to effectively do object detection. And so if you're doing object detection, our data acquisition view allows you to draw bounding boxes. But for image classification, we just support the single label for the whole image.
Okay. And the last question we have is, I think you pointed out earlier that Himax basic board is available on SparkFun for $65. So Guy is wondering if he wants to get the more advanced board you mentioned at the beginning with more capabilities. How do people get these advanced boards? Where and how much it costs, like more?
Yes, I will have the link for it. I don't have it at the moment, but I will pull that up at the end of the presentation, and then I'll put it in the chat.
Okay, well, thank you, David. And thank you again for this presentation and tutorial. So I think it's been quite instrumental for people to understand what the capabilities are of both the Edge Impulse and Himax technologies, and I'm sure they have a better idea how to use it now and where to get these boards and technologies. So let me finish with acknowledging our sponsors again. So I think this is the list of sponsors, and I think we have them also one by one. So it's ARM, Software and Hardware Foundation for tinyML. ARM is an executive sponsor. Next is Edge Impulse. I think we know quite a bit about Edge Impulse now. Thank you, David. And thank you for the sponsorship to Edge Impulse. Next is Himax. Again, Himax develops quite advanced low power AI vision sensors. And next is Intel. I think they had a similar tutorial last week, and the information is available on the tinyML YouTube channel now. So if you're interested in learning more about the Intel platform, I would encourage you to go to the tinyML YouTube channel, which is youtube.com/tinyml, and watch a video there. Next is Qualcomm. It's the company I work for. We do a lot of AI here for different type of hardware technologies, all the way from tiny to server. And that's my last slide. Thank you again for joining this presentation, and thank you for your interest in the Vision Challenge. I think we look forward to your submissions. The deadline is August 20th, so there is still time for submissions. I think there are quite a few already submitted. So, and if you have any questions, you can always contact us. And thank you, David, for this very interesting and informative session.